Alright, so now let's take a look at section 2.6. I want to take a look at rational functions. So a typical rational function is a polynomial function over another polynomial function. So it's a quotient of two polynomial functions. Now in this particular section, we'll take a look at the domain of the rational function, the vertical, horizontal asymptotes of the rational function, and sketch the graph of the rational function. We're just going to go through the procedure on how to sketch the graph and sketch the graph of the rational function with a slant asymptote. We get to all these different definitions later. Okay. And we use the rational function to model and solve real-life problem. Okay. Introduction, let's take a look at how we define the rational function. So rational function is the quotient of the polynomial functions. So basically, both numerator and denominator. Numerator is a function of, it's a polynomial function. And then denominator is also a polynomial function. So it's a polynomial over polynomial. And one thing is the denominator cannot be zero, right? D of x, denominator d of x cannot be zero. Okay. It's like implied domain, right? So basically you can utilize that to find the domain of the rational function. So now in general, domain of the rational function includes all real numbers except x values that makes the denominator zero. So if you're setting d of x not equal to zero, so basically you get a domain. So it's all real numbers except whatever number give us zero in the denominator. And let's take a look at this function, f of x equal 1 over x. If you look at it, so we just set the denominator in order to find the domain. It should be denominator not equal to 0. That means domain is all real numbers except 0. If you put in the interval notation, equivalent to this, negative infinity to 0, union 0 to infinity. So that's a typical interval notation. And interval notation is more widely used. Yeah, that's how we find the domain. Okay, and to determine the behavior of f of x near these excluded values, so just pick some values from the left hand side of the 0. Let's say picking negative 1, negative 0.5, negative 0.1, negative 0.01, negative 0.001, and you plug into the function f of x equal to 1 over x. For example, if you replace x with negative 1, so f of negative 1 becomes negative 1. If you plug in negative 0.5 here, you get negative 2. You plug in negative 0.1 here, you get negative 10. Okay. Plug in negative 0.01, you get a negative 100. And then plug in negative 0.001 here, then you get negative 1000. So as you can see, when the x gets infinitely close to 0, f of x approaches negative infinity. Okay. And on the right hand side, similarly, you're going to start picking the number 1, 0.5, 0.1, 0.01, and 0.001. And then all these numbers, find the y values with the corresponding x values. You get out of this. Similar trend here, you're going to see that when x approaches 0 from the right, this is right hand side. This is left. Then f of x approaches positive infinity. Okay, that's like the aim behavior, right? When x approaches 0 here. So that's why x can never be 0, right? If x is 0, then it becomes undefined. The function becomes undefined. All right, as you can see, if it is negative infinity, positive infinity, it becomes vertical asymptote as well. So this is typical vertical asymptote. A vertical asymptote is defined in this particular setting. Okay, so vertical asymptote for this function is x equal to 0. Okay, so as x approaches 0 from the left, f of x decreases without boundary, without bound. And in contrast, when f of x approaches 0 from the right, f of x increases without boundary, right? Without bound. So that means x equals 0, which is y-axis here. So this y-axis is what we call the vertical asymptote. X equals 0 is the same thing as y-axis. Okay. So that's how we find a vertical asymptote, by setting the denominator equal to 0 to find a vertical asymptote. Meanwhile, you can also find the domain for rational function through this process. Okay, so let's take a look at vertical and horizontal asymptote in more formal way. Okay, so in the previous example, the behavior of f of x, remember we're doing f of x equal to 1 over x. And when x approaches 0 from left and right, f of x approaches negative infinity when x approaches 0 from the left. So 0 minus here indicates approach 0 from the left. You're also going to need this in calculus 1, right? This kind of notation is very important when you get to the limit in calculus 1. And 0 plus here indicates approach 0 from the right. And now, when x approaches 0 from the right, f of x approaches positive infinity. So increase without bound, or decrease without bound. Then we call x equals 0 the vertical asymptote, right? So this is what we call the vertical, y-axis is vertical asymptote. And the x-axis, we're using y equals 0 to represent, and the horizontal asymptote here is x-axis. Because if you look at this curve, it gets infinitely close to x-axis, but never touches it. Same thing for vertical asymptote, f of function f of x gets infinitely close, but never touches it. Okay, so that's exactly the notion of the vertical asymptote, horizontal asymptote is a line or curve. The graph of function gets infinitely close, but never touches it. And same thing for horizontal asymptote, I just explained it when x approaches negative infinity, then f of x approaches 0, right? When x approaches positive infinity, then f of x approaches 0. Okay. And then y equals 0 becomes horizontal asymptote. And y equals 0 is exactly the x-axis. Alright, that's how we interpret horizontal asymptote. And definition of vertical and horizontal asymptote, if line x equal to a. So for vertical asymptote, we always have the same form, right? If it's x equal to a constant, it's a vertical asymptote, then when f of x approaches, when x approaches a, meaning when x approaches asymptote, the f of x approaches plus minus infinity, right? Either one of that. Could be either approaches positive infinity or negative infinity, or both. Okay. And line y equal to b is a horizontal asymptote. When x approaches positive or approaches plus minus infinity, the f of x and the y value approaches constant number b. So typically horizontal asymptote will look like y equal to a constant. Yeah, we look at the detailed calculation later. Okay, so if you analyze all these graphs for the first function, f of x equal 2x plus 1 over x plus 1. And if you look at it, this is a vertical asymptote. And the way how we get a vertical asymptote by setting x plus 1 equals 0, then subtract 1 from both sides of the equation, x equals -1. And that's how we get a vertical asymptote. I'm using abbreviation v dot a dot. So that's vertical asymptote. That's why x equals -1 is a vertical asymptote here. As you can see, when x value gets infinitely close to -1, the y value approaches is equal to here, approaches positive infinity, right? This is positive infinity on top, and this negative infinity on the bottom. Also, from the right, when x value gets infinitely close to -1, then the y value approaches negative infinity. And this is a vertical asymptote. For the horizontal asymptote, it's y equals 2, and the way how we get to 2 is by just dividing the leading terms. So y equal to, drop the constant, right? Divide the leading terms, you get y equal to 2. And that's why y equal to 2 is the horizontal asymptote. And if you look at it, when y value approaches, you see y value approaches infinity right here. Y value approaches infinity, then the x value approaches x value approaches 2, right? So that's a horizontal asymptote. Yeah, and similarly right here, if you just look at the second function, then f of x equal to 4 over x squared plus 1. There's no vertical asymptote because x squared plus 1 will never be 0, right? It's always going to be greater or equal to 1, so it's never going to be 0. So there's no horizontal asymptote, no vertical asymptote. That's what I mean. Asymptote. But that's horizontal asymptote because when x approaches infinity here, if you look at it, when this x approaches infinity, plus minus infinity, then 4 over infinity plus 1 will become 0. So if you look at it, f of x will become 0. That means y equal to 0, and y equals 0 is x-axis. So here the horizontal asymptote is y equal to 0, and that's how you analyze it. Okay, and right here, this one has a vertical asymptote at x equal to 1 by setting, if you setting x minus 1 equal to 0, you get a vertical asymptote 1. Right, that's B, vertical asymptote. And horizontal asymptote, similarly, when x value approaches in plus minus infinity, then 2 over infinity minus 1 square, it becomes infinity. So 2 over infinity becomes 0. So the horizontal asymptote here is going to be 0. So that means y equals 0 is a horizontal asymptote. As you can see from the graph, horizontal asymptote is x-axis, which is y equals 0. And when you sketch the graph, and this vertical and horizontal asymptote becomes important curve or line to separate the graph. This is a typical hyperbola, right? And then if you look at this hyperbola, f of x equal 2x plus 1 over x plus 1, then the vertical asymptote here, vertical asymptote is x equal -1, and horizontal asymptote, the easiest way to do it is just drop the constant, taking 2x over x, you end up with 2. So y equal to 2 is a horizontal asymptote. But if you look at the previous example, f of x equal to 1 over x, that's what we call a hyperbolas, and a horizontal asymptote is x-axis, y equal to 0, vertical asymptote is x equal to 0. Okay. Because 1 over infinity will give us 0, that's how we get horizontal asymptote y equals 0, and setting x equals 0, you get a vertical asymptote. And it's quite special graph. Alright, so now let's take a look at vertical and horizontal asymptote of a rational function. Again, for rational function, is a quotient of the polynomial function over polynomial function. And typically, you could just take a look at leading term here. Okay, so leading term is the main concern. So basically, the remaining of term won't matter because the leading term has the biggest power. So the biggest power will determine the long run behavior of the graph. So now when you analyze it, you can just look at the leading term, comparison of leading term. So typically, the graph of f of x is a vertical asymptote at the zeros of d of x, meaning you setting d of x equal to 0, you get a vertical asymptote. Yeah. And the horizontal asymptote have 3 different scenarios, right? First, so the power here determines, how the horizontal asymptote plays out. So, for example, if let's say we have a rational function when n smaller than m, so 2x squared plus 1 over 3x cubed. Okay, something like that. So if you look at it, when the leading power on top, right here is 2, on the bottom is 3. When the leading power on top is smaller than the leading power on the bottom, so y equals 0, the x-axis becomes horizontal asymptote. You can perform this analysis, f of x. So drop the constant on top. So you get 2x squared over 3x cubed. If you simplify, it will become 2 over 3x. And now here, when x approaches plus minus infinity, then you have a number divided by infinity. A constant over infinity will become 0. And that's why f of x equal to 0 becomes horizontal asymptote. That's the same thing as saying y equals 0 becomes horizontal asymptote. And y equals 0 is the x-axis. Okay, that's how you analyze it. Now, second example could be if when the leading power on top, leading power on the bottom are the same. So let's say we get a 2x cubed plus 1 over 3x cubed. Now, leading power on top, leading power on the bottom are the same. And similarly, when you perform analysis, we just dropped the constant. So you get 2x cubed over 3x cubed. As you can see, the leading power can cancel, x cubed can cancel, so you can end up with 2/3. 2/3 is exactly the coefficient, the quotient of the coefficient on top and bottom. So it becomes an over bm, right? This becomes the ratio of the leading coefficient is the horizontal asymptote. But you can always follow the analysis I just did here to help you understand why they end up with the 2/3 as a horizontal asymptote. And the third scenario is when the leading power on the top, let's say, is 2x cubed plus 1 over 3x squared. Now when you analyze this, meaning the leading power on top is bigger than the leading power on the bottom, so you drop the constant as well, 2x cubed. The reason we can drop the constant because when x approaches infinity, then 1 is irrelevant, right? It's like 1 is like nothing here, so you can easily just drop it. Infinity is something, something imaginary number, but it's like increase without boundary. So that's why any constant compared to infinity is nothing. Okay, so you simplify, you get 2x over 3. As you can see, when x approaches plus minus infinity, that will become infinity, because 2 times infinity over 3 will remain infinity. So infinity does not exist, so that's why we say that there's no horizontal asymptote here. So the comparison of the powers on numerator and the power on denominator will determine the horizontal asymptote. So there are three general procedures, also scenarios you should follow to find that. So now let's take a look at this. For example, find all vertical and horizontal asymptotes of the graph of each rational function. For part A, right? Let's look at part A first. For vertical asymptote, you're just setting x squared denominator equal to 0, and right here we could use a Soviet quadratic equation, so equal to 1. You take in the square root from both side equation and put plus minus on the right. Then we end up with a vertical asymptote, x equal plus minus 1, right? We got it. So this is our vertical asymptote. And for horizontal asymptote, a very similar analysis. From earlier demonstration. So again, you keep the leading term on top, which is 2x squared, leading term on the bottom, because when x approaches infinity, this -1 becomes irrelevant. Okay. So if you reduce it, simplify, you get 2, right? That means f of x is same thing as y equal to 2 is the horizontal asymptote. Right here, when the power are the same, the power of leading term on top and the power of leading term on the bottom are the same, the quotient of coefficient becomes the horizontal asymptote. Okay, that's a general guideline to find a vertical horizontal asymptote. Yeah, so if you look at the graph, basically according to what we find, x equal plus minus 1, that's vertical asymptote. And this is what the graph look like. So as you can see, these two vertical asymptote and then the horizontal asymptote separates the graph in 3 different regions, right? Actually divides a Cartesian system into 6 regions, 1, 2, 3, 4, 5, 6, and then the graph of the rational function is located on 3 of them. One here, and then one here, right? In 3 different regions out of 6 total regions. So horizontal asymptote, vertical asymptote sets the boundary for the rational functions in terms of the graph. And let's look at the part B. So similarly, let's find a vertical asymptote. Very similar. We just set in the denominator equal to 0 and solve for x. And right here is a factor variable. So when you factor that, it's x minus 3, x plus 2 equal to 0. And you set each linear factor equal to 0 and solve for x. For first one, x equal to 3, when you add in 3 from both sides of the equation. Second one, x equal to -2. Yep. So 2 vertical asymptotes. And for horizontal asymptote, practically, as I mentioned earlier, you just dropped out of these remaining terms, right? Drop it. Keep the leading term on top, leading term on the bottom. And that's the simplest way to solve it in terms of finding a horizontal asymptote. And when you divide it, it becomes 1. F of x equal to 1 is the same thing as y equal to 1 because f of x is equal to y. So y equal to 1, that's a horizontal asymptote. Okay, so that's how you find vertical and horizontal asymptote. And that's just a recapture of what we did so far. So now let's look at the sketch in the graph of the rational function. So we're just going to run through the procedure here. First of all, when we have a rational function, step number 1 is simplify function f of x if possible. Right? Let's say if you could factor and cancel terms, that would be good on both top and bottom. And also second step, find and plot y-intercept, right? By evaluating f of 0, meaning setting x equal to 0, find f of 0, and find a y-intercept. So technically, by setting x equals 0, you find a y-intercept. And the third step, find the numerator, find the 0 of the numerator, and then by solving the equation nx equal to 0. And that's how you find the x-intercept. Okay. Yeah. So x-intercept is setting y equal to 0. Right. And y equals 0 is the same thing as n of x equal to 0. Because if you look at it, y is nx over d of x. You set that equal to 0 and make it proportion, cross multiplying, you get nx equal to 0. That's why you only need to set n of x numerator equal to 0 to find the x-intercept. Then after that, find the 0 of the denominator. That's how we find a vertical asymptote. Okay, by setting n of d of x equal to 0, we get a vertical asymptote. And then find a horizontal asymptote using the rule, right? We talked about earlier. And then find a horizontal asymptote and plot at least 1 point between and 1 point beyond each intercept and the vertical asymptotes. Okay, and then use a smooth curve to connect the graph, and they also use the vertical horizontal asymptote to set the boundaries. And that's a typical procedure of graphing a rational function. And the concept of the test intervals, we're going to take a look at the test intervals in a bit. Could be extended to graphing of rational functions. To do this, you need to find all the x-intercept, and then use the step to separate the domain into different intervals, and then we go from there. Okay, now let's take a look at how we sketch this graph. First of all, let's go through all these detail and calculations, right? Let's start with the y-intercept. Now, first of all, you check if you can simplify. And in this example, I don't think we can simplify, so we leave as it is. Now, the step 1 is find the y-intercept by setting x equal to 0. And when x equal to 0, then y equal to 3 over 0 minus 2. Then becomes negative 3 over 2. So the y-intercept turned out to be 0 and then negative 3 over 2. Okay. And do we have an x-intercept? Let's see. Is setting y equal to 0, meaning setting g of x equal to 0. Same thing as y equal to 0. So 0 equals 3 over x minus 2. And if you turn into proportion, cross multiplying, you get a 0 equal 3. That's never going to happen. That means we do not have x-intercept here. So the graph of function doesn't meet with the x-axis. The third step is find the vertical asymptote. So we're setting the denominator equal to 0, we get x equal to 2. And that's vertical asymptote. And the very last step, I mean not the last step, fourth step, find the horizontal asymptote. As I mentioned, you just drop on the bottom, drop the constant, right? When x approaches infinity, negative 2 becomes irrelevant. So 3 over infinity. So here when x approaches plus minus infinity, then this thing will approach 0. That means y equal to 0, which is x-axis, is the horizontal asymptote. Yeah. The next thing is the testing in intervals. So you look at the x value here, all the x value, just 0 and 2, right? So we're going to use those two. So the domain here should be, okay, domain is negative infinity to positive infinity except 2. Okay, so if you want, you could just separate into 2 intervals and test each one of them. Right, so negative infinity to 2. We can also include this 0 here. If you put 0 right here, so we could end up with 3 intervals. So first interval, second interval, and the third interval. Alright, so I'm going to redo the interval quickly, really quickly. So test interval goes here. So first one is from negative infinity to 0. Second interval from 0 to 2. Third interval is 2 to infinity. Okay. And then we're going to pick test value from each interval. Meaning you just pick a number from the interval. First one I'll pick negative 1 because negative 1 is within the interval, right? Just pick a number in the interval. Okay. Second one I'll pick 1. Third interval I'll pick 3. And theoretically, any number in the interval is good. Yes. And then let's find what is test values for each, the sign of f of x. And the last step is conclusion. what we know about the graph of the function. So f of -1, you plug into the original function f of x equal to 3 over x minus 2. So it's going to be 3 over -1 minus 2, which is -3. So 3 over -3 it turned out to be -1. So that means it's definitely negative. So if it is negative, y value is negative, it's below x-axis. That's indication of this calculation here, below the x-axis. Second interval f of 1, so 3 over 1 minus 2, so 3 over -1. So that's still -3, still negative. So this part of the graph is still below the x-axis. Okay, and the third interval f of 3 is 3 over 3 minus 2. So it's 3 over 1, definitely positive. Let's indicate this part of graph is above the x-axis. All right. So now this is what they call the test intervals, right? So you get some order pairs from each interval and start sketching a graph. Meaning from the first interval, I already have one point, one order pair, -1, -1. And you can get some more order pairs, right, to get a graph. Now let's talk about a slant asymptote. Okay, slant asymptote. So typically now we have a horizontal, vertical asymptotes, and slant asymptote is something like this, right? This is the typical slant asymptote. Meaning remember that when there's no horizontal asymptote, then typically we have a slant asymptote. Then slant asymptote exists. Also, technically speaking, we're using the long division to find the slant asymptote. We learned it in the earlier section, long division. And it's a typical case when the n is bigger than m, meaning the leading power on top is bigger than the leading power on the product. So if you look at this one, function f of x equal to x squared minus x over x plus 1, we know that the power on top is greater than power on the bottom, so we know no horizontal asymptote. Now in this case, we will have slant asymptote, and this is actually the slant asymptote right here. Dashed line on the graph. This is slant asymptote. Okay, we do have vertical asymptote, which is -1, right? X equal -1 by setting the denominator equal to 0. Okay, and then I'm going to show you the detailed technique how to find the slant asymptote, like this particular problem. So as I mentioned, using long division. Okay, so x squared minus x plus 0, right? Put in the constant. So this one will go here, and x plus 1 goes here. Now let's divide into that using long division. X going to x squared is x. Okay, x times x is x squared. X times +1 is +1x. Now you find the difference. Okay. Now minus x minus 1x is minus 2x. Carry down to 0, right? And x going to -2, x becomes minus 2. Yeah. So negative 2 times x is -2x. Negative 2 times +1 is -2. We cancel the variable x. Now we get remainder 2. 0 minus -2 becomes 0 plus 2 is 2. And the quotient here, this is the quotient. Quotient is what we call the slant asymptote. So here the slant asymptote is x minus 2, y equal to x minus 2. Okay. And this is a slant asymptote, right? just like how you divide the polynomials by the polynomials. You can also use the inverse division here, but long division usually is more convenient. Sometimes, you know, the inverse division fails when the denominator is not a linear term, right? So long division is universal, it always works. Now, when you sketch the graph here, similarly, you're going to find all this detail. You go through the procedure, right? Like step 1, find the y-intercept. Okay, so you setting x equal to 0. Find the y value. F of x is y equal to 0 squared minus 0 minus 2 over 0 minus 1. So it's negative 2 over negative 1. So it turned out to be positive 2. So the y-intercept is 0, 2. Okay. And second step, find the x-intercept. So right here, we're setting y equal to 0, f of x equal to 0. The same thing as saying x squared minus x minus 2 over x minus 1. And that's equal to 0. And you turn it into proportion, cross multiply, and then solve for x. So we get an x squared minus x minus 2 equals 0 times any variable term becomes 0. And factor this, we get x minus 2, x plus 1. And then you end up with a 2 x-intercept, x equal minus 2 equals 0, x plus 1 equals 0. So x equal to 2, x equal to negative 1. Right? So 2 x-intercept. First one is 2, 0. And another one is negative 1, 0. Okay. And then the third step is find the vertical asymptote. By setting x minus 1 equal to 0, we get x equal to 1. That's vertical asymptote. And the horizontal asymptote, there's no horizontal asymptote, but there's a slant asymptote, right? So you're going to use a long division to find no horizontal asymptote. So that means that's going to be the slant asymptote, you're using long division to find it. We'll be able to find that slant asymptote. So let's do it here to show the calculation here. In order to find the slant asymptote, so slant asymptote. So long division, x squared minus x minus 2 divided by x minus 1. So x minus 1 go into that. Should be x here, right? So x squared minus x. When you multiply that, you get to cancel out of that, and then remainder will be negative 2. So slant asymptote is just x, y equal to x. That's why you see y equal to x on the next slide. With the slant asymptote right here. Okay. And they also test interval, right? Based on the, so basically we have negative infinity to infinity, and all the x values could be negative 1, and a 2. Okay. And then you'll be able to break into 4 intervals and test each one of them. Okay. And eventually you just get some other pairs, right? Generate some additional points from each interval, maybe 1 or 2 additional points, 1 or 2 additional points, depends on the need. from each interval, and you'll be able to sketch it. Okay, and that's basically when you sketch the graph within each interval, you get this particular graph of rational function.